the first three themes that I want to talk about in this presentation, we can see them up here. The first is that the energy-water relationship and problems is a very, very spatial problem, and I'll go into more depth about that, how regionality and spatial variation is important, and how everything is basically spatially connected for the energy-water nexus. The second theme is about how really we're talking about integrating, at least from a modeling perspective, physical and human systems, and so we have to, get a better understanding of how that is going to work. And the third theme is something that we're working on very strongly right now, is that especially where there's a limited resource like water, there's going to be a very strong competition between these existing and new energy technologies going forward, particularly where some of these new energy technologies are very water intensive, like CO2 capture and storage, biofuels, tight gas, oil shale, tar sands. So this first theme is it's all about the spatial variability or the geography of this energy-water relationship. On a very large scale, you look at the regions within the US, it's a very regional problem. So our solutions going forwards for existing and new energy technologies are very regional. What's appropriate for one region might be entirely inappropriate for another region. So we have to be very aware of this regionality issue, but also something we've done quite a bit of research is even within a particular region there can be a very large spatial variability, and it's something we need to be aware of. For example, on a large unconventional fossil fuel project we were working on in the Upper Colorado, the snowpack was the driving force in terms of the impact of climate change. So, for example, using future projections of climate, there was no overall change in precipitation within our projections, and there was no large change in terms of the river flow across the year, no annual river flow change. But there were very large changes in the snowpack, which changed when you get your spring floods. It basically shifts the hydrograph. And so even though there's no overall change in the water availability in the river, when it is available becomes very important. So it's very important for the agriculture in the region and for some of the existing power generation in the region, and certainly for where the new oil shale development is. So again, that spatial variability within the region it comes out as being very important. And kind of the spin-off of this that is also very important is the spatial connectivity of these systems. Water is kind of the central issue for everything that's going on. Water in terms of hydrology is very spatially connected. Whatever you do at one part in the river will have impacts upstream and downstream in terms of water quantity and in terms of water quality or water chemistry. And we also start to see this interaction between the man-made and the natural systems, particularly in terms of water rights. Even if there is enough water available in the river, there are going to be some changes in terms of impacts from climate change, but also in terms of where these water rights are, especially out west, where we have the first-in-time, first-in-line process for water rights. Where you get those water rights might define how new energy technologies can enter a certain region. So that's kind of the geography of this energy-water problem. The other thing that I mentioned, I'm just following on from this, that the water rights is this interaction between physical processes and the human systems, and so we need to get a good handle on this. And again, I mentioned it already, but water rights are going to be particularly important. We're already seeing, even not thinking about projected climate change, even not thinking about population growth, and not even thinking about these water-intensive, low-carbon energy resources and technologies we're talking about, we already have pressures on our energy system. We've already seen I think there's a power plant out in New York that's going through the recertification process, and it's either having troubles or it failed its recertification process because they couldn't guarantee they had access to water. In Texas, we've seen several gigawatts of power right now under threat due to the drought conditions. Out east in the Georgia area, we've seen nuclear power plants struggling to operate either due to drought or particularly in terms of water temperature. They have a limit on what temperature they can discharge water at, and often the water coming in is already exceeding that level, at which point it's very difficult to be running your nuclear power plant. And so the idea is we're already hitting these issues, these physical human issues, and so we need to get a good handle on modeling these, because going forward we are going to have increased pressures, water consumption for population growth, and these new energy technologies. So this is something we really need to be thinking about, and we've heard it already mentioned this morning. We need to think about the other part of the energy-water relationship, where we need energy to start moving water around. We already see it in the Upper Colorado River Basin, where we did this oil shale study where we're seeing water piped over the Continental Divide. We have issues in California where I've seen estimates of 5 or 6% of the GDP or the GSP for California is devoted to moving water around that state. And so we're going to have to start thinking and modeling more about how we're going to be managing this energy-water relationship. And then this third theme that I'd like to talk about is there is going to be an interaction between these energy technologies existing and new energy technologies going forward. And this interaction will often be where there is a limited resource. This interaction will be a competition. We've started to look at kind of at the basin scale. Let's say you have the opportunity for CO2 capture and storage to reduce your CO2 emissions. You're interested in things like tight gas, and maybe you're interested in biofuels. And what we'll start to see is there's going to be competition for limited, in this case, water is the limited resource. I mean, we're going to have to start making decisions on what we would like to do. We can't do everything. We can't capture all the CO2 from our PC power plants. We can't convert all of our marginal lands to biofuels. We're going to have to start looking and modeling this this trade-off. And and again, I mentioned already some examples of where water is already a limiting resource on power production. And things, I think even hydrofracking, some of it has been curtailed in Texas recently because of the drought. We're already seeing these limitations. We're going to see more of these limitations, and we're going to have this trade-off, particularly with future water-intensive, low-carbon technologies. And so we need to get a better understanding and a better way to be making decisions for these limited water resources. The point of this slide is what our perspective at Los Alamos, or one of our perspectives, is that there's a whole range of models out there for existing and future energy productions, and these models, they stretch right from the left-hand side of this slide. We can look at models that go right down to the power plant, looking at the fuel coming in, emissions, water use, right down at that very small scale at the power plant. We can do the same thing for dedicated biocrops, and we have very specific models. And then right to the right-hand side, and the very opposite end of this spatial scale, we have very large-scale models like IGSM and GCAM, which are Office of Science models, and they look at energy technology and other things at the global scale. GCAM, for example, it's this great model. It can look at what is the impact on the climate by converting a large proportion of the area to biofuels, and you start to see that you might even get a 0.5 degree centigrade cooling of the atmosphere globally just because of this wide-scale planting of dedicated bioenergy crops. But what we start to see in the middle of the slide is somewhere in the middle we get less models that start to less models helping us understand what is the interaction between water and energy, and that's where we've really been focusing. And our argument is this is not the only scale that we need to look at, but it seems to be a scale where there's a dearth of information right now at this what we call the basin scale. Let's see. Okay, yes, this basin scale where a lot of these interactions start occurring between energy and water and land and CO2. So there aren't many models that's really capturing this. On a regional level, what kind of decisions should we be making about future energy technologies? Should we be focusing on, for a particular basin or a particular region, should we be focusing on biofuels, on CCS, on wind, solar, whatever it is? This is the level where we see the impacts on water, and it's also the levels we'll see where regional climate change has an impact on water supply and other things. And so our argument is, and we're focusing here right now, is that we can do a much better job at the basin scale helping understand what are regional energy technology and fuel requirements. Okay, this is a bit more on the basin scale, and again, this really brings in the theme of spatial variability, spatial distribution, and how everything really is connected, particularly in things like in the sense of water rights. You do have a limited resource, and you have to make decisions. And again, it's really going to be at this basin scale, kind of where the rubber hits the road. What can we do to sustainably and securely produce energy? And finally, it's kind of an odd slide to finish on, but this is more of a personal opinion. There's something called the ecological fallacy, and this came around originally by looking at the 1920 census, and it's all about making an inference of some process that's happening, but making the inference at the wrong scale. So the idea of the ecological fallacy was you look at the 1920s census, and there's a positive correlation between the immigrant population in a state and literacy. And so the ecological fallacy is drawing the inference that because immigrants live in states with higher literacy, therefore the immigrants have a higher level of literacy. And the idea of applying this to water is, we have to be very careful about what decisions we make in terms of scale. And so we've seen in some of our projects, just because at a very large scale you have enough water, the inference you really need to be looking at is kind of down at this basin scale, or looking at the individual operator of a power plant or a farm or a biorefinery or whatever it is, and making sure that we really understanding what's going on at the appropriate scale, and this kind of draws the end to the theme of the basin scale, where we believe we shouldn't be looking at national estimates for water availability or even large regions, but we really should be looking at this basin scale to understand how existing and future energy technologies will be integrated and competing with each other. Thank you.
Thank you very much. Now, with the last but not least distinguished panel member in our panel today, it's my pleasure to introduce to you Dr. Les Shepard. He is the director of the Institute for Conventional and Alternative and Renewable Energy and holds USAA Robert F. McDermott Chair in the College of Engineering at UT San Antonio. Formerly with Sandia National Lab, for 28 years, Dr. Shepard was responsible for energy, water, and nuclear non-proliferation activities there. Let's give him a warm hand.
Well, good morning. And I noted Abbas actually said last but not least, but clearly less. Sorry, I just had to pick it up a little bit here this morning. Anyway, it's really great to be here in West Texas, in southern New Mexico, and it's also great to actually have an opportunity to interact with my colleagues and friends from the University of Texas at El Paso, New Mexico State, the work program, and other colleagues, as I've spent a lot of time in this part of the country over the course of my career. So it's great to be back home. Thank you so much for the invitation to be here. I should also point out that for those of you who are relatively new to this region, you sit within 30 miles of the global center of green, Hatch, New Mexico. And so it's great to be here for that purpose as well, because the chili is just not quite as good as you drive 6 hours to the east from here.